All right, let's take a look at Unit 1, Atomic Structure and Properties. We're still working on moles and molar mass. Remember, our learning objective is to calculate the quantities of a substance or the relative number of particles using dimensional analysis and the mole concept. And our last essential knowledge for this learning objective is the idea of the molar mass, that every mole must have a certain mass. Now, the way we defined a mole was the number of atoms in exactly 12 grams of carbon-12. And it's this 12 grams that I want to focus on because it establishes a new relationship between mass and moles. 1 mole was equal to 12 grams. And this relationship extends to all other elements as well. So this idea is called the molar mass, the mass in grams of 1 mole of any element or compound. And for an element, the molar mass and the atomic mass are the same numerically. They're just different units. So when I look at a periodic table box, the 1.008 is the atomic mass of one hydrogen atom in AMUs, or atomic mass units. But it's also the molar mass, 1.008 grams for an entire mole of hydrogen atoms. So that molar mass is the same numerically, it just has a different unit of grams now, or grams per mole. So if I asked you what the molar mass of nitrogen is, all you have to do is go to nitrogen and see that it's 14.01. If I ask you for the molar mass of cobalt, you just need to go to cobalt and see that cobalt has a molar mass of 58.93 grams per mole. Now, compounds are a little different. Compounds are collections of atoms that are chemically combined. So the molar mass is just going to be the sum of all the atoms. So if I take an example like methane, which is CH4, it has 1 carbon and 4 hydrogens. I have to add up all the atoms together. So there's a 12 and 4 ones. We'll get about 16.04. Now you give it a shot. What's the molar mass of carbon dioxide? Hopefully, you got about 44 grams per mole. What about the molar mass of water? Hopefully, you got about 18 grams per mole. And again, we're just finding the elements and adding up those atoms. So these conversions are life in chemistry. They allow me to keep track of the number of atoms going into a reaction, coming out of a reaction. 1 mole is 6.02 times 10 to the 23rd particles, and 1 mole has a molar mass in grams per mole, which we can typically find on the periodic table. Now, let's look at an example. How many grams of aluminum need to be massed out to prepare a 2.35 mole sample of aluminum? We're going to underline, circle, square. We're going to set a plan to go from moles to grams. And to do that, I'm going to need the molar mass of aluminum. So that's going to be 26.98 grams per mole. Dimensional analysis starts with what you know, 2.35 moles. I'm going to convert the number of moles to grams using that molar mass. And I'm going to get an answer of 63.4 grams of aluminum. Let's take a look at another example, but let's do it for a compound. How many moles of water are in a 78 gram sample of water? Ooh, I also changed the plan. We're going from grams to moles this time. So underline, circle, square, underline 78 grams. How many moles is my question. My substance is water. I know that I'm going from moles, well, grams to moles, sorry, error there. Molar mass of water is what I'm going to need. The molar mass of water, sum up all the parts, and I'm going to get 18.016. Set up my dimensional analysis, 78 grams of water to start, 18 grams of water in 1 mole, and we'll get a final answer of 4.33 moles. Now, the main ideas are, mole is used to make counting atoms easier. We're going to count those atoms by using the masses of the samples and using the periodic table to figure out how many grams there are per mole. If I can keep track of that, then later on when we're planning reactions, we'll be able to make sure that what we need is going in and what we get out is what we expect.